Alright, volumes of solids with known cross sections. I typed out a lot of details on this one because I wanted you to have something to refer back to with some explanations. But we're going to follow very similar steps in all of these problems. Let's go ahead and just kind of read through this. I want to remind you guys that the definite integral works by calculating the sum of all the areas of an infinite number of rectangles. So really we add up all these infinite heights, right? But we're adding up all these infinite areas of rectangles underneath the curve, and that gives us our total area underneath the curve. Well, what if instead of adding up the area of infinite rectangles, we instead add up the area of infinite cross sections to a solid? So what is a cross section to a solid? So just kind of briefly, let's go over here and just kind of sketch that out. Let's say you have a cylinder, right? I'll just go like that. And if you were to have a cross section, kind of something like this, well, the cross section here would be this circle, right? So we did a cross section of a circle. So this is a pretty simple solid, though. It's a cylinder, and the cross section is a circle. All right. Well, we can have cross section of more complicated solids, though, and we could still calculate their volume using calculus. So we're instead going to add the area of infinite cross sections. So just like with this cylinder, we could add up all these infinite circles, the area of all these infinite circles, and that would give us the volume of the cylinder. Well, we're going to do something very similar. We're going to add up all the area of infinite cross sections, but these solids are going to be a little bit more complicated in shape than just like a cylinder or a sphere or something like that. So let's walk through this example together, and so you can kind of see what's going on here. So first off, they just say, suppose there exists a solid whose triangular base is enclosed by the graph y equals negative x plus 1. We happen to have a graph already here, so that's super helpful. The y-axis and the x-axis. So here's the y-axis and the x-axis. So this is the base of a solid. Cross sections that are perpendicular to the x-axis are semicircles. So that means like it popping out of the screen here are semicircles because this is a three-dimensional figure. So I'm going to do my best to kind of sketch that. Right? And then there'd be like another one popping out here, another one popping out here, and so on. Remember, this is a three-dimensional shape. I'm not really good at drawing it, but you could kind of see that we're going to get kind of some shape going on here, right? Some kind of like a cone, like half a cone, but it's flat on the bottom type shape. And we have infinite semicircles popping out of this thing, right? Maybe it would just make more sense for me to just fill these in. So how can I calculate the volume of this solid all the way from 0 to 1? Well, first we sketch a graph of the base, which we've done. And then the second step is find a formula for the area of any one cross-section in terms of either x or y. Usually we want it in terms of whatever the shape is perpendicular to. So for example, this thing is perpendicular to the x-axis, so we want it in terms of x. So how can we find an area of this semicircle? Well, first off, the area of a semicircle is just half the area of a circle, so we have this guy, pi halves r squared. But remember, our cross-section is perpendicular to the x-axis, so we need an equation in terms of x. Well, this is the diameter, right? This function here gives us the diameter. So negative x plus 1 will give us the diameter, but our formula is in radius. So we need something for the radius. So it's simply the height of the function divided by 2, right? Divide the diameter by 2. So here's what the radius must be, right? If that's the diameter, my y value, whatever y is my diameter, then therefore the radius is the function divided by 2. And so now we have an equation for the area of any one cross-section. Meaning we could find the area of any one of these cross-sections by just plugging in an x. And so we would just plug in our radius into our formula for radius. Boom. And if we simplify this out, we get something like this. Alright. Well, now that we have an equation that represents the area of any cross-section, to find the volume of our solid, all we need to do is add up all these areas of the cross-section from our a value to our b value. Well, in this problem, our a value is 0 and our b value is 1. So we're going from 0 to 1. I put the pi 8 out front because it's a constant, just a coefficient. And here's our function. We take the antiderivative of that, and we get this. And then we could just plug in our 1. Everything else, we don't really need to plug in the 0 because that's a 0, 0, 0. And so when we simplify, we get pi 24ths. Now, that's just kind of a walkthrough of a step-by-step of how you're going to do these problems. So let's go back. Remember, step 2 here was find a formula for the area of any one of your cross-sections in terms of either x or y. See, this is the formula I came up with for the area of a cross-section in terms of x, remember, because it's perpendicular to the x-axis. If these shapes were perpendicular to y, I would need this formula to be in terms of y, and I would need my limits to be in terms of my y limits. So it would go from this 0 to 1. And it just so happens that it goes from 0 to 1 because this is an isosceles triangle as my base. Alright, that's just kind of a brief explanation. I have the steps written out there for you. These steps are universal for these types of problems for the most part, so I think they should help. So let's try and apply it to the next problem on the next page. Suppose there is a solid with cross-sections perpendicular to the y-axis. Okay, that's a huge clue about how we're going to have to set this up. That are equilateral triangles and whose base is enclosed by the function y equals the square root of x, the line y equals 2, and the y-axis. Okay, first things first, before I even read this, we need to sketch a graph of this. Okay, so here's this. The function y equals square root of x looks something like this. The line y equals 2 looks something like this. And we actually know when these two things intersect, because when does y equal 2? Well, it's when x is 4. And so we could just say, hey, this is at 4. And so we know that's when they intersect. And the y-axis we already have. So here's the base of my solid. And out of this thing are equilateral triangles just kind of popping out. Right? So imagine these things kind of popping off the screen because it's a three-dimensional figure. Right? And so it would create this solid. I'm going to kind of draw a dotted line going along the top here. It's going to create this weird shape. Okay. And we're trying to find the volume of this solid. Now remember, step 2, after we sketch a graph, is to come up with a formula of area. And this is where my hint comes in. It says you'll need an equation for the area of equilateral triangles with only its base as an input. Well, let's do that off on the side. We know that the area, having some trouble writing, equals 1/2 base times height. Now, in an equilateral triangle, here's the base, and here's the height. So we need to figure out some way to describe the height in just terms of b, in terms of the base. Well, if this is equilateral, all these sides are b. And if I was to draw the height in, it would cut it into a right triangle where this is half of b and this is half of b. And so this is actually one of our special right triangles going on here, and maybe you remember that pattern, but if not, it's no big deal. We could just use Pythagorean theorem. We know that one side is b squared, or b over 2 squared, plus the other, the height squared, has to equal the hypotenuse squared. And so we get b squared over 4 plus h squared equals b squared. Solve for h, and we would get h squared equals, I'm going to make this common denominators of 4. And so then we get that h squared equals 3b squared over 4. And then we take the square root, and finally we find the height in terms of b. The height equals, let's see, if I took the square root of both of these, you'd end up with b over 2 square root 3. Okay, all that is the height, and this is actually review, kind of something we can do in geometry class. But now if we wanted to find the area of this triangle, a formula for area of this triangle, in just terms of the base, it'd be 1/2 base times the height, which is b over 2 rad 3. We can simplify this whole equation, obviously, and so we would get b squared over 4 rad 3. Okay. So now that we have our area, remember we need this in terms of x or y, and we need it in terms of whichever axis, our cross sections are perpendicular to. And our triangular cross sections are perpendicular to y-axis, so we need this area formula in terms of y. Well, this is the base right here, right? But how would I describe that in terms of y? Meaning I want to plug in a y value, like 2, and I should get this distance here, which is actually an x term. Well, that's going to be described by this function. So we just need to solve it for x, right? Because this is the distance x right here. Always this is, if I plugged in a y value, I would just get this distance x. So I could just square both sides, right? So y squared equals x. And so since this base is the same thing as x, if I wanted to plug in a y squared for b, I could. And so I get that the area actually equals y squared over 4 rad 3. Now, I should be able to plug in any value here, right, a 1, a 1/2, for y, and I get the area of that cross-section. But, remember, I don't want the area of just one cross-section. I want the area of all of these cross-sections, right? I want to add up all these triangles. So to do that, I'm going to take the integral. And this integral happens to be in terms of y, so my volume equals, and the y's go from 0 to 2, and I could simplify this function. I'm going to write the rad 3 force in front because it's really just a coefficient, and y squared squared is y to the 4th dy. Now I'm ready to actually calculate the volume. All I'm doing again is I'm adding up the area of all of these cross-section triangles between 0 to 2. So let's go ahead and give that a shot. If I did the antiderivative of this, the rad 3 over 4 comes out front. The antiderivative of y to the 4th is y to the 5th over 5. And we're evaluating this from 0 to 2. So this is equal to rad 3 over 4. This is 2 to the 5th over 5 minus 0 to the 5th over 5. This, of course, is just 0, so it's not really relevant. All right. We have rad 3 times 2 to the 5th is 32. And 4 times 5 on the bottom is 20. This obviously reduces. We could take a 4 out of both of these, leaving you with an 8 and a 5. And so I could write this as 8 rad 3 over 5. And that would be the volume of this interesting solid created by these parameters as a base with equilateral triangles. Kind of crazy, I know, but if you follow those 3 steps that I laid out there and just repeat that process, you can do these problems. Alright, see you guys on the next video.